Hi, this is Mr. McConley here, and we have BKW General Physics class today. And we're going to be talking about oscilloscopes. So what I have here for you to look at is an actual, not an actual, but a picture of what an oscilloscope might show you. Now, oscilloscope is like a large box, and this box takes electrical inputs from a circuit or from an electrical device, and it shows them in terms of what they look like as a wave. So this one you can see has peaks and troughs. It's kind of in the shape of a sine wave, but since it has points, we call it a triangular wave. Now on an oscilloscope, there's two different main controls or knobs that we're going to talk about: the volt per division knob and the time per division knob. And those are going to allow us to figure out quite a bit about the waveform, and I'm going to teach you how to do that. So this is just a paper and pencil version. I'm at home, so I don't have a real oscilloscope that I can show you. If you want to look one up online, you can find one easily. You can also think of, if you've ever seen like a scan tool in a car automotive repair shop that might be able to keep track of the voltages with what's going on in the car, like a snap-on tool. You could also think of a heart rate monitor that you might see in a hospital. These are types of oscilloscopes. They take electrical impulses and they show them on the screen as a waveform. All right, so let's get down to business as to what we're doing here. I'm just going to turn on one more light. There's a little bit of a shadow going on. I'll turn this radio off so we don't get distracted by that. All right, that's a little bit better. So if this is the waveform that is given to me by the oscilloscope, there's a few things I have to do. The first thing I have to do is I have to take a look here on the vertical knob, which is the volts per division, meaning every one of these boxes in the vertical direction, see vertical direction, each box represents a certain amount of volts. How much? Well, if the knob is set right here, now newer ones would be digital. This one has an actual knob you turn because it's representing an old-fashioned type of oscilloscope. But this says that each of these boxes is worth 0.05 volts. And I'll just write per box so you remember what we're talking about. So each one of them is worth 0.05. The other side here is pointing to a 2, so you immediately like, oh, it means that each box is worth 2, but there's a unit here, looks like a funny looking U, which is called a mu, Greek letter mu seconds. What that means is 2 times 10 to the negative 6 seconds. So each one of these boxes is worth a very small amount, 2 times 10 to the negative 6. And further, what I want to tell you about this is that, in fact, this is a horizontal or a side-to-side scale. So this time we're counting boxes this way. So the left knob was counting boxes up and down, and the right knob was counting boxes side to side. All right, so let me give you an example of what a question or what the questions might ask. I'm just going to go through this with you and show you how it's done. So this is a question that was asked about this particular one. It says, name the shape of the wave. Like I said, it's a sine type of wave, but it's got points, so it's called triangular. How many volts per division, or volts per, we could say instead of division, we could say volts per box. And we found a moment ago, by looking at the left knob, that it was 0.05. Okay, good. So we fill that in here. How much time per division do we have? And we can see that, according to the right knob, each box is worth 2 times 10 to the negative 6, or 0.000002 seconds. So we fill that in right here. now we get to the point where we actually have to calculate a little bit, and we want to figure out, if we're looking at this waveform, how much voltage is that representing from peak to peak voltage. So the way they ask you is they say the voltage of this source is what? And here's how you do it. You're going to first look at your picture and you're going to say, okay, this is the lowest and this is the highest point. And I'm only worried about up and down or vertical. So if I start here and I start counting up, I have 1, 2, 3, 4, 5 boxes. Can you see that? Starting here, 1 full box, 2, 3, 4, 5 boxes. All right, so I have 5 boxes. And we determined a little while ago that each box was worth 0.05. So 0.05 volts per box. So now I just take out my handy dandy calculator. I multiply 5 times 0.05, and I will get that this picture represents 1/4 of a volt. That's what I have shown right here. 5 boxes at 0.05, you times them, you get 0.25 volts in total. The next thing that's always asked is, it says, what's the period? The period. Now, period means time for one cycle. That's what period means, time for one cycle. So in this case, back to the picture, we're looking at, if we start right at this point right here, and we start following the pattern, when does the pattern start to repeat itself? Now at first you might think, oh, it starts to repeat there, but not really, because we're going up, we're going down. Now we might be at the same height, but we're going the opposite direction. When it really starts to repeat itself is right there. So from this point here to this point here, that's when the pattern starts to repeat itself. This is one complete cycle. And if we want to know how much time that is, again, we got to count boxes, but this time we're counting boxes horizontally or left to right. So we start here. 1, 2, 3, 4, 5, 6. I get that there's 6 boxes. So I come over here, I say, okay, there's 6 boxes. Each box, remember from what we figured out a while back, is 2 times 10 to the negative 6 seconds. So each box is worth a very small amount. When you times 6 times 2 times 10 to the negative 6, 6 times 2 times 10 to the negative 6, you're going to get still a pretty small number. You're going to get 1.2 times 10 to the negative 5 seconds. That means that each wave, the time it takes for each wave to go by, is 1.2 times 10 to the negative 5. Or could be written, of course, this way. If you take the decimal point, you move it 1, 2, 3, 1, 2, 3, 4. I need one more 0 there. So it could be also written as 0.000012 seconds. So it's a very small amount of time. Whatever this is that we're looking at is happening very quickly. The voltage is only 1/4 volt, and it's happening very quickly. All right, so, and of course, back to my work paper, that's what I've shown right here, 6 boxes, I times it. There's my answer. The last thing that they ask about is the frequency. Now what frequency means, frequency is how often you are repeating the pattern. So it's not the time, but it's how often. We talked about this earlier in the year when we talked about electrical outlets, and we said electrical outlets had a frequency of 60 hertz. So I wonder what the frequency is of this waveform. Now, I'm just guessing by the very short amount of time that it's going to be a high frequency because it's repeating itself very quickly. So here's the way you figure it out. If you want to know what the frequency is, all you're going to do is take the number 1 and divide it by the period or the time for one wave that we just found out a little while ago. So we're going to take the number from up here and we're going to put it on the bottom. So 1.2 times 10 to the negative 5 seconds. We're going to take and do 1 divided by that number, and that will tell us the actual frequency. When I do that on my calculator, I get a huge number, 83,333, and the units are hertz, because hertz, as you recall, means that many things per second. So this means per second. So 83,000 hertz is the frequency, and as you can see, that's what I did on the bottom of the page. So, just to recap, we've taken this waveform, which represents an electrical signal of some sort, I don't know what it is, and we determined it was a triangular wave. We determined the voltage by looking at the boxes top to bottom. Then we determined the period by looking at boxes left to right. Then we did the frequency by taking 1 and dividing it by the period. If all that makes sense, then what I'm going to have you do in a little while, I'm going to send you another example, which is actually just the next example down on this little page, and I'm going to have you try it on your own. So for today, this is Mr. McConley with General Physics class.